Long before anyone built a clock, people still had to manage time. Early societies watched repeating patterns in nature: sunrise and sunset, lunar cycles, seasonal shifts, and star movement. At first, these patterns were enough for agriculture and ritual life. But as settlements grew, social life became more complex. Farmers, priests, rulers, and traders needed shared timing that could be referenced publicly, not just felt privately. That need created a major shift. Time moved from being an environmental experience to being a social resource. Once a community depends on coordinated action, rough intuition is no longer enough. You need tools that translate cosmic cycles into practical intervals. This is the core problem behind the history of timekeeping. How do you convert nature's rhythm into a dependable system for everyday decisions? Every invention that follows, from sundials to atomic clocks, is a different answer to that same challenge. Sundials were one of the first successful answers. In ancient Egypt, and later in Babylonian and Greek contexts, a simple object casting a shadow became a measurable guide to daytime progression. The concept seems basic, but it was revolutionary. A sundial externalized time. Instead of relying on memory or guesswork, communities could point to a shared instrument. That changed civic behavior. Public timing made it easier to standardize work periods, ceremonies, and governance routines. But sundials also revealed the limits of early time technology. They require sunlight, proper orientation, and local calibration. Cloud cover, indoor settings, and nighttime made them useless. Their value was high, but conditional. Still, their deeper contribution was cultural. They normalized the idea that time can be read from a device. Once that mindset took hold, people began expecting measurable structure in daily life, and that expectation drove the search for clocks that worked beyond the sun. To overcome daylight dependence, ancient engineers turned to continuous processes, especially water clocks. Instead of tracking shadows, they measured time through controlled inflow or outflow of liquid. Water clocks appeared in several civilizations, including Egypt, Babylon, Greece, and China. Their biggest advantage was flexibility. They could function indoors and after sunset, making them useful for courts, rituals, and administration. But this came with engineering trade-offs. Flow rate is difficult to keep constant. Pressure changes as water level changes, and environmental factors like temperature can affect behavior. So early designers had to think in terms of regulation, vessel geometry, and calibration. That marks a significant intellectual step. Water clocks are not just instruments, they are process control machines. They show an early understanding that if natural markers are unavailable, you can build a physical system that progresses at a roughly known rate and infer elapsed time from that process. This logic becomes a recurring theme in all later clock development. Different regions expanded timekeeping in distinct ways. In China, incense clocks used predictable burn rates to mark intervals, blending practical timing with ceremonial culture. In the medieval Islamic world, water clock design reached remarkable sophistication, with complex mechanisms that pushed precision and automation further than many contemporaries. In Europe, the hourglass emerged as a highly practical interval timer, especially at sea where motion and weather could disrupt other methods. These examples matter because they show that clock history is not a single line of genius moments in one place. It is a distributed story of local constraints and creative adaptation. A device's success depended on where and how it was used. A palace instrument, a monastery regulator, and a shipboard timer solved different problems. The best timekeeping tool was often the one that remained reliable in the target environment, not the one that looked most advanced in theory. Mechanical clocks in medieval Europe changed the scale of time coordination. Weight-driven systems with Virgin-Foliot control converted stored energy into repeated motion, allowing clocks to run independently of sunlight and fluid flow. Their early social role was often tied to monastic bell schedules, where regular prayer times demanded consistent signaling. But once installed in towers, mechanical clocks became urban infrastructure. Bells synchronized entire communities. Time could now be imposed across space through sound, not just checked visually. This transformed time from local observation into institutional authority. People increasingly lived by externally announced hours. The clock tower became both a technological and political symbol. Someone controls the schedule, and everyone hears it. Mechanically, these clocks were far from precise by modern standards. Socially, they were transformational. They created the expectation that time should be continuous, public, and binding. That expectation paved the way for later precision revolutions, because once society depends on scheduled regularity, pressure grows to make clocks better. The invention of the mainspring in the early 15th century enabled smaller clocks and eventually more personal timekeeping. This was not just a design tweak. It changed who could own and use a clock. Large weight-driven clocks belonged to institutions and fixed places. Spring-driven designs allowed portable forms, moving time measurement closer to individual life. But miniaturization did not automatically solve accuracy. Early portable mechanisms still drifted due to friction, uneven force delivery, and crude regulation. So the central question shifted from how to keep a clock running to how to keep it running at a stable rate. That shift is crucial. Endurance and precision are different problems. A clock that runs all day but loses time unpredictably is only partly useful. As commerce, navigation support, and scientific work expanded, tolerance for drift shrank. The stage was set for a breakthrough based on a new principle, harmonic oscillation as a stable timing reference. The pendulum provided that breakthrough. Observations associated with Galileo highlighted the regularity of pendular motion under controlled conditions, and Christian Huygens turned the idea into a practical clock in 1656. Compared with older mechanisms, pendulum clocks were dramatically more accurate. The significance goes beyond better minute-keeping. A reliable oscillator acts like a consistent heartbeat for the entire mechanism. Once the heartbeat stabilizes, all derived measurements improve. This raised standards across science, administration, and technical practice. Better clocks meant better astronomical observations, tighter coordination, and stronger confidence in measured intervals. It also illustrates how progress in timekeeping depends on coupling theory and craft. Understanding periodic motion is one thing, building robust hardware that preserves that regularity in daily use is another. The pendulum era succeeded because both came together. It replaced rough mechanical pacing with a physics-informed regulator, shifting clockmaking toward true precision engineering. Precision exposed new error sources, especially temperature effects. If components expand or contract, timing changes. In the 18th century, makers like John Harrison and George Graham worked on compensation strategies to limit thermal drift. These refinements became urgent because of navigation. After the 1707 Scilly disaster, pressure intensified to solve the longitude problem. Determining east-west position at sea required accurate time comparison between local observations and a reference meridian. In simple terms, if your clock is wrong, your map position is wrong. And at sea, that can be fatal. Harrison's chronometer work addressed this by producing increasingly stable portable timekeepers suited to marine conditions. The chronometer became a symbol of practical precision, not laboratory elegance, but survivable reliability under motion, humidity, and temperature variation. This episode shows how clock innovation is often accelerated by high-stakes consequences. Maritime trade, naval strategy, and human safety all depended on better clocks, so society invested heavily in making time portable and trustworthy. In the 19th century, electric clocks introduced a new architecture. Electricity made it easier to link timing systems and distribute reference signals over distance. Instead of many isolated clocks drifting independently, networks could be coordinated around stronger standards. This foreshadowed modern synchronized infrastructure. Then quartz technology, especially from the 20th century onward, delivered a major leap in practical accuracy and scalability. Quartz crystals vibrate at highly stable frequencies when electrically stimulated, providing consistent oscillation with less mechanical complexity than traditional high-precision movement systems. Quartz was not only more accurate for many uses, it was easier to mass-produce, cheaper to maintain, and ideal for integration into electronic systems. That combination made precise timekeeping widely accessible. It also tied clocks directly to the broader rise of electronics, where frequency control is fundamental. So quartz did more than improve watches, it became part of the timing backbone for communication, measurement, and computing technologies. Wristwatches show how timekeeping moved from institutional control into personal habit. Their military usefulness helped drive adoption, and after World War I they became mainstream in civilian life. Over time, materials and technologies expanded their capabilities, non-magnetic designs, battery power, solar options, transistors, and plastics each increased practicality for different users and contexts. A wristwatch became both tool and identity object, blending utility with style and status. But the next shift changed behavior even more. Since the early 2010s, smartphones and smartwatches have become dominant everyday timekeepers. The clock is now embedded in connected systems that also manage reminders, communication, navigation, and health tracking. We no longer consult time as a standalone metric, we interact with an ecosystem that constantly interprets and acts on time. This integration increases convenience, but it also tightens the grip of scheduling on attention. Modern timekeeping is less about reading an hour hand and more about living inside synchronized digital prompts. At the highest level, atomic clocks define today's practical precision frontier. By using predictable atomic transitions as frequency references, they achieve stability measured in tiny fractions of a second per year. This is not over-engineering for its own sake. Atomic standards calibrate other clocks and support systems where timing errors cascade quickly: satellite navigation, telecom synchronization, financial sequencing, scientific instrumentation, and power network coordination. In effect, atomic clocks are quiet infrastructure for global modernity. Most people never see one directly, yet countless daily services depend on them. Viewed historically, atomic clocks continue the same pattern that began with sundials: identify a regular physical process, convert it into a reference, and organize society around it. The process has become incomparably more precise, but the core ambition is ancient. We keep refining time because coordination complexity keeps rising. Better clocks did not just tell us what time it is. They made larger, faster, and more interconnected forms of civilization possible. The full arc of timekeeping reveals a feedback loop between technology and culture. Societies demanded coordination, so they built clocks. Better clocks then enabled denser coordination, which created demand for even better clocks. From shadows to water, gears to pendulums, springs to quartz, and atoms to global timing networks, each leap reduced uncertainty and expanded what people could organize together. But there is a trade-off. As precision increases, expectations harden. Punctuality, productivity, and responsiveness become stricter social norms. Timekeeping devices did not merely record civilization's pace, they helped set it. That is why this history still matters. Every glance at a phone clock is the endpoint of thousands of years of engineering, observation, and institutional adaptation. The modern timestamp feels effortless, but it rests on a deep lineage of problem-solving across cultures. Understanding that lineage turns a familiar daily act into a larger insight, measuring time more accurately has been one of humanity's most consequential ways of reshaping how we live together. If you found this helpful, please like this video and subscribe for more explainers.